Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of the precise definition of a limit for Calc 1, or differential calculus. We have already gone through several topics in the precise definition of a limit. Specifically, we have talked about the actual precise definition of a limit, finite limit at a finite point. We have proven limits for linear functions and limits for non-linear functions. That was the last video. And now we're going to take some side cases. Well, one specific side case. And then in this video, we're also going to extend and just do, actually, maybe I'll just keep this for a single side case. So let's just keep this kind of a short video here. Proving single-sided limits. A single-sided limit is something like this, right? You've seen this before. The limit as x approaches 2 from the right-hand side. And it has to be approaching 2 from the right-hand side, by the way, in this situation, because let's pretend it was approaching 2 from the left. Then you're essentially plugging in numbers like a 1.99 or, something below 2. And when you do that, 1.99 minus that 2 right there becomes negative. And then we would have a negative underneath this radical, which is a problem. So it is a requirement that x is approaching 2 from the right to keep that radical as a real number. So how does that adjust our epsilon delta proof? Well, if you look in a textbook, it does have actually a sub case for this, but this is one of those, and I'm kind of reading off the screen here, but really this is truthfully what I feel. This is one of those rare moments where I believe some hand waving is perfectly fine. You're already learning the topic that to many might seem very challenging. There's no need to complicate it more by using a textbook version of the precise definition of the limit for a single-sided limit. So instead of worrying about the textbook definition, I will just say, use the same epsilon delta proof that you would normally use. Now, if you're an instructor and you're watching this, your hackles are probably raised. You're probably like, what is going on? No, there is something wrong. You can't always use the epsilon delta proof for single-sided limits. But you would also agree with me that students are going through a lot with epsilon delta proofs. And as long as they can really truly understand an epsilon delta proof, we really don't need to belabor the issue with a single-sided limit style proof as well. So let me at least showcase to students why the single-sided limit presents an issue. So here is my actual precise definition of a limit applet, and in Desmos, that is. And you can see that I'm not actually dealing with the square root function for a very specific reason here. It's the same style of function though. The argument is still x minus 2, and it's still subtracting 1 on the outside, just like the problem that we were just presented with was the square root of x minus 2 and then minus 1. And in the problem we were presented, the center of what x was approaching was 2. Same thing here. So from the precise definition of a limit, somebody had handed us an epsilon neighborhood, right? And our goal is to shorten up or tighten up that delta neighborhood so that all x values from within our delta neighborhood here lead to y values that are within that red band. And here's the problem with this epsilon delta neighborhood for single-sided limits. Delta, in fact, all neighborhoods, so if I say the word neighborhood about 2, that implies that not only do you have x values to the right of 2, but you have to consider x values to the left of 2. And that's where the single-sided limits fall apart, because you cannot, for example, if I change this function to the square root of x minus 2, you cannot have a value to the left of 2. There's no such delta neighborhood that has an x value to the left of 2 there, because it causes, within our function itself, a negative number underneath the radical. And so it does not make sense, because our function doesn't exist in this entire delta neighborhood. The delta epsilon proof falls apart officially. However, I will just tell you that you could still use the epsilon delta proof for the most part. You could still say, I'm going to squeeze in that delta neighborhood really tight here, and eventually it'll be good enough. Now, notice it doesn't say great job in my applet here, and that's because the function doesn't exist on the left-hand side. And so there's no actual true way to have the epsilon delta proof work as written. However, again, I don't want to overcomplicate what's already complicated for a lot of students. Instead, I'll just say, listen, you've already gone through a big war here. I'll give you a win on this one. And what does that mean in this case? It just means that you'll prove this just like it were a regular epsilon delta proof. You're just going to say, for any epsilon somebody hands me, some red band, horizontal band, plus or minus epsilon from your y value of -1 here, you should be able to find, that's a terrible there exists. Let me zoom in a little bit. You should be able to find a delta neighborhood centered at x equals 2 in this case, such that as long as the distance between x and your center at 2 is less than delta, that should imply the distance between your function and the limit will be less than epsilon. So again, this actually doesn't look any different than all other epsilon delta proofs. In fact, it's just as easy as the linear ones. So let's go ahead and go to the right and start our scratch work. And within the scratch work, or maybe within the proof itself, we'll see what issues creep up because we're dealing with a single-sided limit. It won't be terrible though. So remember how this works. We want to assume we've arrived at that ending statement there. I need to say, hey, you know what I've done? I've achieved the fact that my difference between my function and my limit in absolute value is less than epsilon. So let's go ahead and assume that part. And that's what I have written here. Let me go ahead and just point out our function is the square root of x minus 2 minus 1. And our limit is a -1. And we're assuming that's less than epsilon. And then over to the right, I'm just going to mention what I want. In the end, I want to arrive at the distance between x and 2 to be less than delta. So I want the distance between x and 2. Let me write that over here. The distance between x and 2. I want that to be less than some constant. And if you look at what we've assumed, well, that's the square root, the absolute value, sorry, of the square root of x minus 2. All right, -1 plus 1 cancels, less than epsilon. Something you need to note here, and this is kind of where our statement about the one-sided limit, x is approaching 2 from above, and all that silliness comes into play. Technically speaking, that absolute value is positive, or sorry, the square root is positive. There's no need for the absolute value. However, if somebody told me the answer is absolute value of 3 when the answer was supposed to be 3, I would say, well, technically you're correct, right? 3 is the same thing as the absolute value of 3. So there's nothing wrong, except for that it's somewhat elementary, but there's nothing wrong with leaving the absolute values there. Remember what I want. I want to get the absolute value of x minus 2. So I'm going to square both sides. Here I go. Absolute value of x minus 2 is less than epsilon squared. I just squared both sides here. And I've successfully arrived at a bound for the absolute value of x minus 2. That will be my choice for delta. So let's go ahead and start the proof, because once you've found the delta, you can start your proof. All right. So here goes my proof. I'll just write proof here. I like to write my proofs in black ink for some weird reason. And when you write your proof, remember, you're just going to copy the definition. So given any epsilon greater than 0, we will choose delta to equal epsilon squared. Well, if that's the case, then as long as the distance between x and 2 is less than delta, and by the way, technically speaking, this is where a professor might yell at me and say, wait a second, there's no need for the absolute values there. You're absolutely right. If x is approaching 2 from the right-hand side, those absolute values are unnecessary. But just like the absolute value of 3 is the same thing as 3, I'm pretty okay with leaving the absolute values there. So I'm okay with that. All right. Anyhow, if it is the case that the absolute value of x minus 2 is positive but less than delta, then I'm just going to go back to my work, my scratch work on the right hand side there, and I'm going to say, well, then the absolute value of x minus 2 must be less than epsilon squared, because that's what we chose delta to be. Which implies if I take the square root of both sides, this is true. Now, again, this is where somebody might say, aha, but you can't take that square root inside the absolute value unless you are 100% certain that x is greater than 2. Well, I am. I'm 100% certain that's true because that's what the limit is. So again, I'm doing a little bit of hand waving here. I'm not really rigorously justifying this because I think you guys have gone through quite a bit, and I don't mind that you kind of take this little shortcut. Anyway, finally, I will just say this implies it's the absolute value of the square root of x minus 2 minus 1 minus a negative 1, because I'm copying my scratch work over on the right hand side there. And then somebody says, well, what does that mean? And I say, well, you know what that means? Because this piece right here is my function, and this piece right here is my limit L. So given any epsilon, ladies and gentlemen of the jury, you know I did that last time. So ladies and gentlemen of the jury, if somebody hands me an epsilon, I don't care what it is, I am going to choose my delta neighborhood to be of radius, your epsilon squared. And they say, why? And I say, well, I'll show you why. If x is within my delta neighborhood of 2, so if it's really close to 2, then we can all guarantee that x minus 2 in absolute values must be less than epsilon squared, because that's what I chose delta to be. And they say, okay. And I say, but then I'll take the square root of both sides. And they say, fine. They say, fine. And I say, but then I'll subtract 1 and add 1. And they say, I don't know why you did that. And I'll say, because this is your function and this is your limit. So I have successfully, independent of, not independent actually, but based upon whatever epsilon you hand me, as long as I make that choice for delta, my function is super close to the limit. How close? Within the epsilon neighborhood of the limit. And so therefore, we have proven the limit. It is very fast if you don't worry about the single-sided limit proof that the authors usually like. Now, I'm not discounting the single-sided limit proofs. I just think that they're a little more overcomplicated than they need to be at this point. You've already gone through massive head trauma just trying to get to this point in Calc 1. I think this should be counted as a win for you. This is the only thing I want in this video, by the way. So proving single-sided limits kind of work like this. I'm going to stop the video right now, and the next video will finish out this introduction to the precise definition of a finite limit.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.